Okay, here we are in chapter 5, stereoisomerism, and in the first part, all we're looking at is across the alkene. Is it either cis or trans across the double bond? So to look at that, all you need to do is imagine a line, draw a line through the two carbons of the double bond, and look where are the big groups on either side. On the left side, we have a hydrogen in the isopropyl. On the right side, we have a hydrogen in that big carbon chain. And so on the left side, the isopropyl is bigger than a hydrogen because it's the carbon versus hydrogen. On the right side, it's carbon versus hydrogen. So it's the big group there. So this one is trans across the alkene. The next one, part B, if you look down the double bond, there's a hydrogen on each end. We can't say what it is because we have the same thing on one end. Two of the same thing on one end, so we don't have to say cis or trans. On the next one, if we draw in the hydrogens and then look at the double bond, the two big groups are on the same side, so this is cis cyclohexene. Okay. Now, if we go down to the bottom and start talking about stereochemistry, to have a stereocenter, we have to have 4 different groups on one carbon. So if we look at the first one here, we have a 5-carbon chain with on carbon 2, we have the methyl, we have the propyl, we have a hydrogen, and we have the OH. So we have 4 different things on this one. This will have a stereocenter right here. On the next one, we have a hydrogen, an OH, an ethyl to the right, and an ethyl to the left. So we only have 3 different things. So this is not a stereocenter. It does not have a chiral compound because we have to have 4 different things for there to be a chiral compound. So how do we name things? We need to figure out the RS, and for that RS, to assign RS, it is best to have the lowest priority group in back. Okay, there are ways to do it without getting it in back, but I prefer to teach it in a way so that you always do the exact same thing to answer a problem. So the first thing you do is make sure the lowest priority group is in back. In this one, the hydrogen is, so we don't have to worry about it. And we have the OH as priority 1. Then we have a carbon and a carbon, so we have a tie, and then we have hydrogen, which is priority group number 4. Between the 2 carbons, the one on the left has 3 hydrogens, the one on the right has 2 hydrogens and a carbon. So the one on the right would be a higher priority than the one on the left. So this would be priority 2 here and priority 3 here, where it goes like that. Okay, so this is counterclockwise, so this center is S. Now we have to get the lowest priority group in back to assign R and S. So to get there, we'll talk in the next couple of pages. We have on how to do that. So here we have some compounds, and all we have to do is assign RS. We don't have to name them. Okay. So the first one, we have the oxygen, the ethyl, the methyl. It is S. The second one, if we look at what we have compared to the first one, okay, there's a shortcut sometimes we have when there are 2 groups in the exact same spot. The methyl and the ethyl are in the exact same spot off of the stereocenter, and 2 groups, the OH and the H, are flipped from one going back to one going forward. Anytime 2 groups are the same and 2 groups are different, it has to be the mirror image, the enantiomer of it. Okay, so this one has to be R, but can we prove it to ourselves? The hydrogen's not in back, so we need to rotate the hydrogen in back, rotate the OH up here where the ethyl is, rotate the ethyl down where the hydrogen is. So that gives us this. And when we go from oxygen to ethyl to methyl. The hydrogen doesn't matter because it's in back. We go from 1, 2, 3. It's clockwise, so it is R. The next one, the hydrogen's not in back, so it needs to move in back. The OH up here, the tritium down here, leaving the deuterium alone. D, OH, T, and H. Highest priority group is the oxygen, second is tritium, third is deuterium. 1, 2, 3. It is R. Okay, now if we look at the next one again, it's not drawn with the lowest priority group in back, so we need to rotate 3, holding 1 steady, so the T stays steady. You have the D, you have the OH here, and the H here, and it goes from OH, T to D, so it is also R. Okay, now I will admit when I do these problems, when I make them up on the computer, I do not try to make them a certain thing. I just draw them and they end up what they are. So don't think they're going to be a bunch of R and a bunch of S and they'll evenly be distributed. There's might be one R and a bunch of S's, or one S and a bunch of R's. It just depends on how it comes out. The next one is drawn so that the hydrogen's in back, so we just have to go from the heaviest, bromine, chlorine, fluorine, it's R. Then if we look at it compared to the next one, the bromine and the chlorine are in the same spot. The hydrogen and the fluorine are flipped, so this has to be S, but we can prove it to ourselves by redrawing it. One thing has to stay steady. Bromine, fluorine, chlorine, hydrogen. This one goes counterclockwise. It is S. The next one, the hydrogen's not in the back, so we need to rotate the hydrogen in back. We could put the hydrogen there, the bromine where the chlorine is, chlorine where the hydrogen is. So we have chlorine, bromine, hydrogen. So it would be bromine, chlorine, carbon. It's R. Okay. Then the last 3 get tricky in that you're going to try to add up the weight of the whole group. It doesn't matter what the group is. We start with the atom off of the stereocenter for hydrogen, carbon, carbon, and nitrogen as our 4 groups. So nitrogen is the heaviest, hydrogen is the lightest, so nitrogen's 1, hydrogen's 4, and then we have the 2 carbons with a tie. Of the 2 carbons, we have 1 with 3 bonds to oxygen and 1 with 3 bonds to hydrogen, so it's going to be nitrogen, the acid, then the methyl, like that, but we got to rotate the hydrogen in back. So hydrogen or the nitrogen, nitrogen or the methyl, methyl or the hydrogen, so we have CH3, COH, because we didn't move that one, NH2, hydrogen in back. The hydrogen doesn't matter, go 1, 2, 3, it's S. Now, I know you're sitting there thinking, but you didn't do the one above it. Now, for this, does it matter what the group is once you know the priority? And the correct answer is no, it doesn't matter what it is. So, in that ring, you don't have to worry about redrawing it so that you get the carbon lowest priority group in back. You just think about what they are. So if we draw it bromine 1, chlorine 2, and then between the 2 carbons, this carbon has 2 hydrogens and a carbon. This carbon has 2 hydrogens and a carbon. They're tied. We have to look one more. The second one down on the right has a hydrogen and 2 carbons. On the left, it has 2 hydrogens. So this would be 3. This would be 4. So we need to rotate 4 in the back. 2 where 1 is, 1 where 4 is, 1, 3 stayed put, 4, and 2. So we're going 1, 2, 3. It is clockwise. It is R. Now the next one, the hydrogen has to go in back, the amine up there, the methyl in front, N, methyl, hydrogen, acid, 1, 2, 3, it's R. And then the last one, the highest priority group, is the oxygen. And then we have 3 carbons, so the carbons are tied. We have to look at what's off the carbons. So the first one, the top one, has 3 oxygens. The amide is 2 oxygens and a nitrogen. And then we have the alkane with 2 hydrogens and a carbon. Now on that, we all know that oxygen is heavier than nitrogen. So number 2 is the acid, number 3 is the amide, number 4 is the alkane. So we could leave number 3 where it is, rotate number 2 down in front, rotate number 1 up, and get number 4 and back, and it goes 1, 2, 3, it is S. Okay? So try those. If you have models, make a model of each one and try it out and see what you get. Now, the next one, 2 to the N stereoisomers, where N is the number of stereocenters. So this one has 1, 2, 3. So obviously 2 raised to the 3rd power for the number of possible stereoisomers. Okay, and there's enough of that. Then optical activity. If we put a sample in a polarimeter, we can see what happens with it. So we have this equation to give us the specific rotation for a chiral molecule. Okay, and where this is the specific rotation, the alpha in brackets, the alpha is the observed rotation, and then we have it divided by the concentration in grams per milliliter, and the for neat solutions, the density, and L is the path length in decimeters. So we have to be careful about the decimeters. So for this, all we have to do is calculate this being 21.6996 times the concentration, which is the point, where'd it go? 0.8025 grams per milliliter, and that's times the path length, 40 centimeters, which when we convert centimeters to decimeters is 4 decimeters. So when we do this, multiply it out, we get 21.6996 divided by the 0.8025 times 4, which is about 3.2. Okay. Let me get my calculator and give you the exact number. 21.6996 divided by 4 divided by 0.8025 gives us 6.76 if we divide it all out. So 6.76. This is for our sample. Now we're told the pure sample has a specific rotation of 13.52. Calculate the percent EE. So for this, we take our 6.76 divided by 13.52, multiply it by 100, and we get 50, right? 50% EE. What does that mean when you're talking about the percent enantiomeric excess? Okay, so that's telling us that of the pi, half of it is 1 enantiomer, and the 1 enantiomer is plus. of the other half, it's half minus and half plus. So for this sample, 75% plus, 25% minus for our overall mixture. Okay, so when you subtract the 25 from the 75, you're left with the percent EE. Okay, the next one says a sample of 2-bromobutanoic acid has a specific rotation of 14.7 in the negative direction, plus 2-bromobutanoic acid structure shown below has a specific rotation of 39.5. Draw the stereochemical formula for minus. So can we draw the mirror image of this? Hope so. Going to have the ethyl coming towards the mirror, the hydrogen going back, the bromine coming towards, then our acid. So there we have the correct stereochemical formula for minus 2-bromobutanoic acid. Now calculate the percent EE. For that, we know our sample is negative 14.7, and our pure is 39.5. When you do this, multiply by 100. We want to first ignore the negative charge and just deal with all positive numbers because you can't have a negative percentage. But 14.7 divided by 39.5 gives us 37.2. Oops. 37.2. Now this, our pure sample was negative, so this is the negative enantiomer. We have 37.2% more of it than the other. So then think about the pi. 37.2 is negative. The 62.8 is a split between the two, so 31.4 is negative and 31.4 is positive. So the positive one is 31.4 and the negative one is 68.6% of that overall sample. Okay, and anytime you have to draw something, draw it, start with the lowest priority group in back and then put the other three things in so that they go the right way. So here we have the stereochemical relationships between enantiomers and diastereomers. So when we look at this, we need to redraw it, getting the lowest priority grouping back on each end. So we can just rotate the end around, redraw it. So we get the methyl here, the hydrogen here, the chlorine here. On this other end, we have the OH. Whoops. H and the CH3. So on the end with the OH, which is going to be carbon 2, this is going to be 2. The OH is priority 1. This carbon here with the chlorine is 2. The methyl is 3. It is counterclockwise, so it's 2s. And then the carbon with the chlorine is 1. This carbon that I labeled number 2 for the counting the carbons in the chain is going to be number 2. Just happened to fall that way. And the methyl is number 3, so it is 2s, 3s. Okay, then we need to do the same sort of thing for the compounds down below, but we have to be careful because the ones down below are flipped over, so we need to make sure we make this carbon 2, the one with the alcohol, and the carbon with the chlorine, carbon 3. So if we rotate the OH in back, or the H in back, the OH down here, the methyl up there, redraw it, and then do the same thing here, methyl up there, chlorine down here, chlorine, hydrogen, methyl. So the chlorine, the OH is going to be, carbon 2 is going to be S here. Carbon 3 is going to be R. So compound A is a diastereomer where one group is the same and one group is different. It has to be at least one group of each. Okay. Now the next one, if we erase what we drew on the molecule, so we can look at it, carbon 2 is the same between A and B, so carbon 2 in B is still 2s. Carbon 3, the one with the chlorine, okay, looks like it's where the chlorine rotated there, the methyl rotated here, the hydrogen rotated here. It's the exact same thing between A and B. It's just one rotation around the circle to get to where you were. So it has to be the same as B. So it is 3R. So A and B are both diastereomers of one another. A and B are the same thing, but that's not what the problem is asking. It's asking you to compare it to X. Now C, when we look at it, carbon with the OH on it, the methyl and the hydrogen have flipped, so it has to be 2R, and then the chlorine and the methyl have flipped, so it has to be 3S, so it is also a diastereomer of X. Okay, now down here in the bottom part, make a model of these and look at them and prove to yourself that there is a point of symmetry in both of these. Okay, there's a point of symmetry in this one, and one of the last three has not a plane of symmetry, but when you ring flip between the two, I'll give you a hint, it's one of these two. When you ring flip between them, you get the same compound. Okay, so try that and prove to yourself which one of these two is a very large space chiral molecule. This one is chiral, and one of these two is chiral. But I want you to tell me which one, because it may show up on a test one day. Okay, or don't tell me and just be surprised in early October. And then here we are on the last page where we have the discussion about mesocompounds, and mesocompounds are compounds that have a plane of symmetry in them. And to have a plane of symmetry, you have to have the exact same group, obviously, on it. So in A, if we number top to bottom, 1, 2, 3, 4, carbon 2, the bromine, we need to rotate each of them around to get the hydrogen and back to assign RS. So when we do that, we're going to end up with the bromine here, the hydrogen here, the hydrogen here. Can't draw it there, sorry. Let me draw it down lower. If we draw it here, and for this, the neat part about it is if we draw one of them and we understand what's going on, we don't have to do the same thing for all of them to assign RS. So here is A, and it's going to be bromine, this crap on the bottom, the methyl. So carbon 2 is S. Carbon 3 is going to be bromine, this carbon up here, and then the methyl. So it's going to be 3R. Okay. Now the neat part about this is, since we know where things are in compound A, every time carbon 2 looks like this, it has to be 2S, because everything is in the exact same spot, so it's the same center. Now the bottom one, every time our bromine is to the right, it has to be 3R, so this one has to be 2 something 3R, okay, and then these other two, the bromine and the hydrogen, are flipped from the first two, so they're going to have to be 2 something 3S, right? And this one's going to be 2S 3S. Okay, now we got to look at the other center, carbon 2, for B and C, and they are flipped, where the bromine and the hydrogen are opposite of where they were to begin with. So they are both 2R. So A is 2S3R, B is 2R3R, C is 2R3S, and D is 2S3S. B and D are enantiomers, non-superimposable mirror images. Okay, so A and B are enantiomers of one another, or B and D, excuse me. A and C are mirror images because both centers are inverted, flipped, whatever you want to call it. But if we were to number A from the bottom to the top, it would be 2R3S. And if we look at C, lo and behold, that's what C is. So A and C are actually meso compounds. They're the same thing. The mirror image is superimposable. Gotta make sure I say it right. Okay, so the mirror image is superimposable. They're the same thing. Okay, and so then if we look at, this is compound B, same one as up there. It is 2R, 3R, 2, 3 di-bromo-butane. Okay, you have two bromines, it's di, not bi, di-bromo-butane. Okay, and then the bottom one is the flip of that, so it's 2S, 3S, 2,3 di-bromo-butane. Okay, and then how do you convert to a Fisher projection? Think of it as a big roach running across the floor. What do you do to it? You step on it and flatten it out. So when we flatten this out, we just draw it with lines straight across, all showing as if they were in the plane. When we draw a Fisher projection, we are assuming that it is arced away from us, so that top and bottom are, if this is what it looks like from the side, here's top carbon, here's the bottom carbon. We're looking at it from above. It's arcing away from us. Okay, so the things on the side are coming towards us even though they're drawn flat. Okay, and it's just a way to save time to draw things when we show it in the Fisher projection. I prefer to look at them with the three-dimensional drawings, so we won't do a lot of Fisher projections, but there will be some where you may have to convert from one to the other. Okay, if you have any questions about any of this, send an email. Try some of the problems out of chapter 5. Okay, they're all great problems. Okay, and keep working so this section goes well. See you all tomorrow.